Hi. When calculating a limit, the main issue you'll face is dealing with what we call indeterminate forms. These are situations where no standard calculation rules apply, so you'll need to find a way, for example, by reworking the expression to remove the problem. In this video, we'll look at the main indeterminate forms in the context of limits for sequences. And we also see a few examples to understand how to overcome them. We will use very basic techniques, specifically avoiding the use of differential calculus tools, which can be very helpful in handling these situations. For example, let's start with the rules for calculating the limit of the sum of two sequences. So suppose we have two sequences, an, bn, of real numbers, an going to some limit L1 and bn going to a limit L2. Now, the limit of the sum, an plus bn, is the sum of the limits L1 plus L2 in the following cases. First, when both limits L1 and L2 are finite. Second, when one is finite and the other is infinite. So, for example, L1 is plus or minus infinity and L2 is finite. Then the limit is infinity with the sign of the infinite limit here. And third, when both limits are infinite with the same sign. So plus infinity, plus infinity, or minus infinity, plus minus infinity. In this case, the limit is plus or minus infinity with the plus or minus the same sign of the common value of these limits. We have to be careful. These are not new calculus rules, new algebraic rules, because if you think about the number plus itself equal the number, x plus x equal x, holds only for x equals 0. Now, there is just one case which is excluded from this list, which is the case when the two limits are both infinite, but with opposite sign. And this is the case of the form plus infinity plus minus infinity. In this case, we have an indeterminate form. Let's see what does it mean by a list of simple examples. So consider first the case when an is n squared, going to plus infinity, and bn is minus n, going to minus infinity. We do the sum, we obtain n squared minus n, that clearly goes to plus infinity because n squared dominates n. By reverting the two parts, an equal n, going to plus infinity, and bn equal minus n squared, going to minus infinity, we get an plus bn is the opposite of the previous one, so now it goes to minus infinity. Now, if we take an equal n and bn equal minus n, we have again plus infinity plus minus infinity, but the sum is constantly equal to 0, so it goes to 0. So here you can see that the limit can be infinity, plus or minus, or finite. We can also have a case where the limit does not exist. Consider an equal n plus minus 1 to the n, which is a plus minus 1, depending on n even or odd. And clearly it goes to plus infinity. And bn equal minus n, that goes to minus infinity. We sum the two, and we get that the 2n and minus n cancel, and an plus bn remains equal to minus 1 to the n. That, as we know, has not a limit. So as you can see, what can happen is basically everything. Limit infinite, finite limit, or no limit. So this is why we do not have a rule that can say what happens when we have a plus infinity plus minus infinity form. That's why we call it an indeterminate form. However, as these examples show, this does not mean that we cannot determine the limit. In fact, in these few examples, we have been able to discuss, in any case, what happens to the sum an plus bn. Now, there are many other indeterminate forms. For example, which is basically the same of the sum, we have for the difference the form plus infinity minus plus infinity, so the difference between two infinities of the same sign. For the product, we have the case infinity plus or minus times 0. So one factor goes to 0, the other goes to infinity. for the ratio, we have two forms, the 0 over 0 form and the infinity over infinity form. Now, let's see with an example how to handle an indeterminate form with basically elementary methods. Consider the limit for n going to plus infinity of n times root of n fourth plus n plus 1 minus n squared. Let's start the analysis saying that this clearly goes to plus infinity, then the argument of the root clearly goes to plus infinity, and the root will go to plus infinity. Minus, here we have n squared that goes to plus infinity as well, and therefore, as you can see, in the parentheses we have an indeterminate form, plus infinity minus plus infinity. So, to understand what happens here, let's rewrite the expression here, root of n fourth plus n plus 1 minus n squared. Now here we will use simply an algebraic trick, which is to multiply by the sum of these two terms, so the root plus n squared, and divide by the root plus n squared. The point is that here we have something like a minus b times a plus b. So it gives a squared minus b squared, and this makes the root to disappear. So we have, in fact, that when we do the product, the numerator becomes n power 4 plus n plus 1 minus n squared squared, so n to power 4, divided by the sum of these two. Now, here we see that we can first simplify this term. About the denominator, these two terms are not in competition because they both contribute to go to infinity for the denominator. We may observe that inside the root, the dominating term is n to power 4. So if we factorize and take out of the root, we get an n squared factor times root of 1 plus, you see, dividing by n to power 4, 1 over n cubed plus 1 over n to power 4. And then I have a plus n squared. I can factorize the n squared and write plus 1 and put a parenthesis here. Now, this is the reworking of the expression. So now, to understand what happens to the limit, notice also that the numerator is now n plus 1. We can factorize n and write 1 plus 1 over n. This parenthesis is just a quantity that goes to 1. So we can just write a quantity that goes to 1 sub n, divided by an n squared times this parenthesis, which is 1 plus a root. The argument of the root goes to 1, so the root will go to 1 for the continuity, because of the continuity of the root. So this parenthesis goes to 2, so we can write a quantity that goes to 2. Now we still have the indeterminate form here, but in this case, we can directly simplify the terms determining the indeterminacy, and now we have no more an indeterminate form, because this is 1 over n times a quantity going to 1 divided by a quantity going to 2, and clearly this goes to 0. So this is now what is the limit of the round parenthesis term. But this shows that we have now a new problem, because the factor in front is going to plus infinity, and this is going to 0. So we have an infinity times 0 indeterminate form. What we have done is useful to solve this problem, because if we multiply by n everything, so this is just this term, so we have n times, n times, n times. We arrive here, and you see that we can simplify these two, where you can see clearly the form infinity times 0. And now what we obtain is that the limit is 1/2. So this is the limit of the expression we have here. So as you can see, it has been possible to discuss completely all the indeterminate forms and to compute the limit. Good. So what are the next steps? First of all, you should continue practicing how to handle indeterminate forms by doing an exercise of this type, for example, which is similar to the exercise we have done here. Then if you want something more spicy, let's say, you could consider this problem, which is still similar, but now with parameters. So this makes the discussion a bit more involved. And finally, if you want to enter in depth with the comprehension, you should try to prove some general property, as for example, one of the rules I mentioned at the beginning of this video. So when you have a sequence that goes to plus infinity, plus a sequence that has a finite limit, their sum will go to plus infinity. Good luck.